There's a sound in the universe you've never heard, a whisper so faint it travels for billions of years before it reaches us. It's the echo of stars that died long before our planet even existed, their final moments rippling through space as gravitational waves and ghostly electromagnetic hums. These aren't just cosmic footnotes, they're the lingering symphony of collapsing stars, a celestial melody written in the language of physics and time. And today we're going to listen. Picture this: a massive star, burning bright for millions of years, suddenly runs out of fuel. In its last violent act, it doesn't just fade away, it implodes, sending shockwaves through the fabric of spacetime itself. The energy released is so immense, it distorts the universe around it, like a stone dropped into a pond. But here's the astonishing part: those ripples don't disappear. They keep traveling, stretching across galaxies, carrying the story of that star's death to corners of the cosmos we've yet to explore. This is the phenomenon scientists call a symphony of collapsing stars that still echoes through the void, and it's one of the most hauntingly beautiful mysteries in all of astronomy. Why does this matter to us? Because these echoes are more than just cosmic curiosities, they're time capsules. Every ripple, every faint signal picked up by our telescopes holds clues about how stars live, die, and reshape the universe around them. They help us piece together the life cycle of the very elements that make up our world: the iron in our blood, the calcium in our bones, all forged in the hearts of these distant, dying giants. So let's embark on a journey together, tracing these stellar echoes back to their origins. By the end, you'll never look at the night sky the same way again. Every great cosmic story starts in darkness, not the empty kind, but a darkness thick with possibility. Picture a vast, swirling cloud of gas and dust drifting through space for millions of years. It's cold, quiet, and seemingly lifeless until gravity begins its patient work. Tiny particles start to clump together, drawn by an invisible force, growing denser and hotter under the weight of their own gathering mass. This is how stars are born, in the quiet collapse of these cosmic nurseries where chaos gives way to creation. Deep inside these collapsing clouds, something extraordinary happens. As the pressure builds, temperatures soar to unimaginable heights, hot enough to ignite the universe's most powerful engine, nuclear fusion. Atoms of hydrogen, the simplest and most abundant element in the cosmos, are forced together with such violence that they fuse into helium, releasing a burst of energy in the process. That moment when fusion sparks to life is the first true heartbeat of a star. It's the moment a shapeless cloud becomes a radiant beacon, flooding its corner of the universe with light. But here's what's even more remarkable. The size and composition of that original gas cloud determine everything about the star's destiny. A smaller, modest cloud might birth a star like our sun, steady, dependable, burning for billions of years. A massive, dense cloud, though, that's where the real cosmic drama begins. It creates stars so colossal, so ferociously bright, they live fast and die young, their lives measured in mere millions of years instead of billions. These are the stars destined for the most spectacular endings, the ones whose deaths will one day send shockwaves across the cosmos. And just like that, we've come full circle. The birth of a star isn't just about its beginning, it's about the seeds of its eventual demise, written into its very first moments. The same nuclear furnace that gives it life will one day consume it from within, setting the stage for that final, catastrophic collapse. But that's a story for another moment. For now, let's stay here in the glow of creation where stars are just beginning to sing. A star's life is a cosmic tightrope walk, a constant tug of war between the crushing force of gravity and the explosive power of nuclear fusion. For millions or even billions of years, these forces battle to a standstill, keeping the star shining steadily in the void. But make no mistake, this balance is temporary. Every star, from the humblest red dwarf to the most colossal blue giant, is born with an expiration date written in its core. Take our Sun, for example, a middleweight star in the grand scheme of things. Right now, it's in the prime of its life, faithfully converting hydrogen into helium at a rate of 600 million tons every second. That staggering number might sound like a lot, but for a star of its size, it's just enough to keep the lights on for about 10 billion years. And when its fuel finally runs low, it won't go out with a bang. Instead, it'll swell into a red giant, gently puffing away its outer layers into space, leaving behind a glowing ember called a white dwarf, a dense, Earth-sized remnant that will cool over trillions of years, fading into darkness like a dying campfire. But the universe's heavyweight stars, their stories end very differently. Imagine a star 20 times more massive than our Sun, burning through its fuel at a breakneck pace. These titans live fast, shining with blistering intensity, but their brilliance comes at a cost. In just a few million years, they've exhausted their hydrogen, then fused heavier elements like carbon, neon, and even iron in a desperate bid to stave off collapse. And that's when the real drama begins. Once iron starts piling up in the core, fusion can't continue. Iron is a cosmic dead end, absorbing energy instead of releasing it. With no outward pressure left to fight gravity, the star's core implodes in less than a second. The outer layers, suddenly without support, come crashing down only to rebound in one of the most violent events in the universe, a supernova. For a brief moment, the dying star outshines entire galaxies, scattering newly forged elements across space in a fiery farewell. What's left behind depends on the star's original size. Some collapse into neutron stars, city-sized objects so dense, a single teaspoon of their material would weigh 1 billion tons on Earth. Others, the most massive of all, vanish into black holes, warping spacetime itself. But here's the incredible part. Even in death, these stars aren't truly gone. The shock waves from their explosions ripple through interstellar gas, triggering new star formation. The heavy elements they created become part of planets, oceans, and even life itself. And sometimes, if we listen closely, we can still hear their echoes, gravity waves humming through the cosmos, or the faint afterglow of light that's traveled for millennia to reach our telescopes. This grand cycle, birth, life, death, and rebirth, is the engine that shapes our universe. Without the fiery demise of massive stars, we wouldn't have the oxygen we breathe, the gold in our jewelry, or the uranium that heats Earth's core. Every time we look up at the night sky, we're witnessing chapters in a story that began billions of years ago, written in the lives and deaths of stars we'll never see. And somewhere out there, right now, another star is reaching the end of its journey, its final act destined to echo through the cosmos long after its light has faded. The moment a supernova erupts, it rewrites the cosmic landscape in an instant. Imagine a star hundreds of times the size of our Sun, reaching the end of its fiery reign. Its core, now packed with iron, can no longer sustain the nuclear reactions that once kept it shining. Gravity, relentless and unforgiving, wins the battle in a fraction of a second. The star's core collapses inward at nearly 1/4 the speed of light, while the outer layers rebound in a shockwave so powerful, it tears through space with the energy of 1 billion suns. This is the supernova's crescendo, a flash of light so intense it can outshine an entire galaxy for weeks. But the real magic happens in the chaos. The temperatures and pressures inside that explosion are so extreme, they forge elements heavier than iron, gold, platinum, uranium, elements that can't form in the peaceful fusion of ordinary stars. These newly minted atoms are hurled into space at incredible speeds, riding the shockwave like cosmic surfers. Over millions of years, they'll mix with interstellar gas, becoming part of new stars, planets, and eventually the building blocks of life. That ring on your finger, the uranium powering nuclear reactors, even the iodine in your table salt, all of it was born in the heart of a dying star's final, cataclysmic act. Yet the supernova's impact doesn't end there. The explosion sends ripples through the surrounding nebula, compressing nearby gas clouds and triggering the birth of new stars. It's a cosmic chain reaction. One star's death becomes the spark for another's beginning. And sometimes, if conditions are just right, the collapsed core left behind doesn't fade quietly. It might become a neutron star, a spinning, city-sized remnant so dense its gravity bends light into a shimmering halo. Or if the star was massive enough, it vanishes into a black hole, a gravitational pit so deep, not even light can escape. But here's what's truly astonishing. Even after the light fades, the supernova's voice lingers. Gravitational waves, ripples in spacetime itself, radiate outward, carrying the story of that explosion across the universe. Centuries later, those waves might pass through Earth, stretching and compressing our planet by an amount smaller than an atom, yet detectable by our most sensitive instruments. It's as if the star is still speaking to us, whispering its final secrets across the eons. So the next time you gaze up at the night sky, remember, the darkness isn't empty. It's alive with echoes of stars that lived, died, and in their passing lit the way for everything that came after. Not every dying star scatters its remains across the cosmos. Some leave behind something far stranger, a stellar corpse so dense it defies imagination. When a massive star collapses but isn't quite large enough to form a black hole, its core doesn't just fade away. It undergoes one last violent transformation, crushing itself into a sphere no bigger than a city, yet containing more mass than our entire sun. This is a neutron star where matter has been compressed to its absolute limit. Picture squeezing Mount Everest into a sugar cube. That's the kind of pressure we're talking about here. Under these extreme conditions, atoms can't exist as they normally do. Electrons are forced into protons, turning them into neutrons, hence the name. The entire star becomes a single, gigantic atomic nucleus, a swirling sea of subatomic particles packed shoulder to shoulder. A single teaspoon of this material would weigh about 1 billion tons on Earth. But what makes neutron stars truly extraordinary isn't just their density, it's what happens when they start to spin. As the star collapses, it speeds up its rotation, much like an ice skater pulling in their arms. Some neutron stars whirl hundreds of times every second, becoming cosmic dynamos. Their intense magnetic fields, trillions of times stronger than Earth's, funnel radiation into narrow beams that shoot from their poles like interstellar searchlights. When these beams sweep across our line of sight, we detect them as rapid, clockwork pulses of radio waves, X-rays, or even visible light. We call these spinning neutron stars pulsars, and they're some of the most precise timekeepers in the universe. The regularity of these pulses is mind-boggling. Some pulsars keep time more accurately than atomic clocks on Earth. Their rhythms so stable, scientists can detect variations as small as 1 part in a quadrillion. This incredible precision makes them invaluable tools for testing Einstein's theory of relativity. When a pulsar orbits another dense object like another neutron star or a black hole, the subtle changes in its pulse timing reveal how gravity warps spacetime around it. In fact, the first indirect evidence for gravitational waves came from observing a pulsar's orbit slowly decay, exactly as Einstein's equations predicted. But pulsars aren't just cosmic laboratories, they are also celestial lighthouses, guiding our exploration of the galaxy. The Voyager spacecraft carry maps with pulsar patterns, showing Earth's location relative to these spinning beacons. And in 2017, the collision of two neutron stars created ripples in spacetime detected here on Earth, while telescopes caught the accompanying flash of light, a breakthrough that opened a whole new era of multi-messenger astronomy. These ultra-dense remnants remind us that even in death, stars continue to shape our understanding of the universe. They're not just relics of the past, they're active participants in cosmic discovery. They're rhythmic pulses writing new chapters in the story of spacetime itself. Black holes are the universe's most enigmatic final act, a silence so profound, it swallows even light itself. Yet their presence reverberates across the cosmos in ways we're only beginning to understand. When a star many times more massive than our Sun exhausts its fuel, its collapse doesn't stop at a neutron star. Gravity, unchecked, crumples the core into an infinitely dense point called a singularity, wrapped in an invisible boundary known as the event horizon. Cross that threshold and there's no return, not for matter, not for light, not even for time as we know it. But here's the paradox: while black holes trap everything within their grasp, their influence extends far beyond their dark hearts. Picture a bowling ball placed on a trampoline. The heavier the ball, the deeper the dip in the fabric. A black hole does the same to space-time, warping it so severely that nearby stars orbit invisible paths, their trajectories tracing the unseen monster's gravitational pull. Sometimes we detect black holes indirectly, like watching leaves swirl in a hidden whirlpool when stars or gas clouds dance around empty space with frantic, inexplicable speed. And then there are the ripples, when two black holes spiral toward each other in a cosmic dance. Their immense gravity churns spacetime like a paddle through water, sending out waves that race across the universe at the speed of light. These gravitational waves, predicted by Einstein over a century ago, were first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, or LIGO. The signal came from two black holes, each dozens of times the mass of our Sun, colliding over 1 billion light-years away. In their final moments, they released more energy than all the stars in the observable universe combined, all in the form of silent, invisible ripples in the fabric of reality. What's astonishing is how much these echoes reveal. By studying gravitational waves, scientists can hear the universe in a whole new way, measuring the masses of merging black holes, the spin of their orbits, even the texture of spacetime itself. It's like learning to read a new alphabet written in the language of gravity. And sometimes these collisions aren't just black holes. Neutron stars, those dense stellar remnants, can also spiral together, their crashes sparking fiery kilonovas that forge gold and platinum in cosmic quantities, scattering precious metals across galaxies. Yet black holes aren't just destructive, they're also cosmic architects. At the center of nearly every large galaxy, including our own Milky Way, lurks a supermassive black hole millions or even billions of times heavier than our Sun. These giants shape their galaxies from the inside out, their gravity orchestrating the motion of stars and gas. Some actively feed on surrounding matter, heating it to millions of degrees and blasting out jets of energy that can outshine their host galaxies. Others lie dormant, their presence a silent anchor in the galactic dance. So while black holes may be the ultimate silence, they're far from silent players in the universe's story. Their gravity writes the rules for galaxies, their collisions send whispers across spacetime, and their very existence challenges our understanding of physics. They remind us that even in the darkest corners of the cosmos, there's a symphony playing, one we're just learning to hear. Gravitational waves are the universe's most elusive messengers, ripples in the very fabric of spacetime that carry whispers of collisions from billions of years ago. Imagine tossing a pebble into a still pond and watching the ripples spread outward. Now replace the pebble with two black holes, each heavier than 30 suns, spiraling toward each other at half the speed of light. The pond is spacetime itself, and those ripples stretch and compress everything in their path, including the atoms that make up you and me. This isn't science fiction, it's the reality scientists confirmed in 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, captured the first direct evidence of these waves. The discovery was a century in the making. Albert Einstein predicted gravitational waves in 1916 as part of his theory of general relativity, but even he doubted we'd ever detect them. The distortions they create are unimaginably tiny. A passing wave might change the distance between Earth and the Sun by less than the width of a single atom. Yet LIGO lasers, bouncing between mirrors 4 kilometers apart, are so precise they can measure shifts 1,000th the size of a proton. When that first wave arrived on September 14, 2015, it lasted just 0.2 of a second, a fleeting chirp from a pair of black holes merging 1.3 billion light-years away. But what makes gravitational waves so revolutionary isn't just their existence, it's what they reveal. Light can be blocked or scattered, but spacetime ripples pass through everything, carrying undistorted information about their origins. With each new detection, we're essentially tuning into a cosmic radio station, picking up signals from events we could never see with telescopes. Some waves sound like quick chirps, the hallmark of black holes colliding. Others, like the one from 2 neutron stars merging in 2017, come with a fireworks show of gamma rays, X-rays, and visible light, allowing us to study the same event through multiple cosmic messengers. These collisions aren't just spectacular, they're cosmic alchemy labs. When neutron stars crash, the extreme conditions forge heavy elements like gold, platinum, and uranium, scattering them into space. That means the gold in your jewelry was likely born in a cataclysm so violent, it bent the fabric of the universe, and thanks to gravitational waves, we're now pinpointing where and how these elements are made, tracing the origins of the very atoms that make up our world. Yet the most profound revelation might be how gravitational waves let us test the limits of physics. Every merger is a natural experiment, probing Einstein's theories under conditions no lab could ever recreate. So far, general relativity has passed every test, but with more sensitive detectors coming online, we might finally find cracks in the framework, hints of new physics lurking in the echoes of these cosmic collisions. This is the true power of gravitational waves. They've given us a new sense in our exploration of the cosmos. After centuries of studying light, we're now listening to the universe's hidden soundtrack, a symphony written in the language of spacetime itself. And with every new detection, the melody grows richer, revealing chapters of cosmic history we're only beginning to understand. While gravitational waves carry the deep bass notes of cosmic collisions, the universe also sings in higher frequencies blasts of gamma rays, flashes of X-rays, and crackling radio static that linger long after a star's final act. These electromagnetic echoes are more than just cosmic pyrotechnics. They're detailed postcards from the edge of oblivion, each wavelength revealing a different chapter of a star's demise. Take gamma-ray bursts, for example, the brightest electromagnetic event since the Big Bang itself. When a massive star collapses into a black hole, twin jets of plasma can erupt from its poles at nearly the speed of light. If one of those jets happens to point toward Earth, we detect it as a searing burst of gamma radiation, packing more energy in seconds than our Sun will emit in its entire 10 billion-year lifetime. But the story doesn't end there. As these jets plow through surrounding gas, they create an afterglow, a fading firework of X-rays, visible light, and radio waves that can last for weeks. It's like watching smoke curl upward after a cannon blast. By studying these afterglows, astronomers can reconstruct the explosion's geometry, measure its distance, and even identify the heavy elements forged in the cataclysm. In 2017, when two neutron stars collided, telescopes caught not just gravitational waves but also a kilonova, a glowing cloud of radioactive gold and platinum that confirmed these collisions as cosmic foundries for the universe's heaviest elements. Then there are the quieter voices in this cosmic chorus. Radio waves, often emitted by the debris clouds of supernova, can persist for centuries. The Crab Nebula, the remnant of a star that exploded in 1054, still crackles with radio emissions nearly a millennium later, its pulsar heartbeats ticking away like a celestial metronome. Even the coldest stellar corpses, white dwarfs cooling into oblivion, emit faint X-rays as they slowly fade, their light a whisper of the fusion fires that once burned within them. What makes these signals so valuable is their specificity. Gamma rays tell us about the most violent moments of collapse, X-rays reveal the scorching aftermath, and radio waves map the slow expansion of debris. Together, they form a multi-wavelength fingerprint, allowing scientists to piece together stellar life cycles like detectives solving a cosmic murder mystery. And with every new detection, we're not just observing death, we're witnessing the birth of new elements, new physics, and new questions that push our understanding of the universe forward. So while black holes might steal the spotlight with their gravity-defying drama, it's often these electromagnetic echoes that hand us the real treasure, a front-row seat to the intricate, luminous, and endlessly surprising ways stars rewrite the cosmos in their final moments. The universe has a way of turning endings into beginnings where one star's fiery death becomes the raw material for new worlds. Every atom heavier than hydrogen and helium, from the oxygen in your lungs to the calcium in your bones, was forged in the heart of a star or scattered in the aftermath of its explosive demise. This isn't poetry, it's physics. When a massive star goes supernova, it doesn't just vanish. It seeds the cosmos with the very ingredients that make planets, oceans, and life possible. Consider the iron in your blood. It didn't form on Earth. It was created in the final moments of a dying star, where temperatures soared so high that lighter atoms fused together under unimaginable pressure. When that star exploded, it catapulted these newly minted elements into space, where they mingled with vast clouds of gas and dust. Over millions of years, gravity pulled these enriched clouds together, forming new stars surrounded by swirling disks of debris that would one day coalesce into planets. Our solar system is the product of such a cycle, built from the ashes of stars that flared and faded long before the sun even ignited. But the recycling doesn't stop there. Some of the rarest elements, like gold and uranium, can't form in ordinary supernova. They require something even more extreme, the collision of two neutron stars. When these ultra-dense remnants spiral into each other, the resulting kilonova explosion is a cosmic forge, producing staggering amounts of heavy elements in seconds. The gold in your jewelry, the platinum in catalytic converters, even the iodine essential for thyroid function, all were likely born in these violent mergers, scattered across galaxies to eventually find their way into Earth's crust. This grand cycle of creation and destruction isn't just a backdrop to the universe, it's the reason we exist. The carbon in our DNA, the nitrogen in our atmosphere, the silicon in the rocks beneath our feet, all were once stardust, adrift in the void until gravity and time brought them together. Even the water in our oceans carries a stellar legacy. Its hydrogen atoms date back to the Big Bang, while its oxygen was forged in the hearts of ancient stars. So when you look up at the night sky, remember, you're not just a spectator to the cosmos. You're part of it, woven from the same materials as the stars themselves. The universe doesn't waste a single atom. It rebuilds, recycles, and reinvents, turning the echoes of dying stars into the building blocks of new life. And somewhere out there, right now, another star is reaching the end of its journey, its final act destined to fuel the next chapter in this endless cosmic story. There's an invisible hand guiding the cosmic symphony, one we can't see, touch, or even directly detect, yet its fingerprints are everywhere. Dark matter, the universe's most elusive architect, doesn't shine, absorb, or reflect light. It doesn't interact with the ordinary stuff that makes up stars, planets, or us, except through gravity. And that gravitational pull is rewriting the rules of how galaxies dance, how stars are born, and even how the echoes of collapsing stars travel through the void. Picture a spinning galaxy. Based on the visible stars and gas alone, the outer edges should move slower than the center, just like planets farther from the sun orbit more slowly. But that's not what happens. Galaxies rotate as if they're encased in an invisible halo of mass, something we now call dark matter, a substance that outweighs ordinary matter 5 to 1. Without it, galaxies would fly apart, their stars scattering into the darkness. This hidden scaffolding doesn't just hold galaxies together, it shapes how they form in the first place. When the universe was young, dark matter's gravity acted like a cosmic net, gathering clouds of hydrogen gas into dense knots where the first stars could ignite. Those early stars, in turn, became the seeds for galaxies, meaning dark matter didn't just influence the universe's structure, it orchestrated it. Even today, when massive stars collapse into supernova or neutron stars, their gravitational waves ripple through this invisible framework, subtly altered by the unseen mass they pass through. It's as if the universe's grand symphony is being played inside an enormous, resonant chamber we can't see, but whose presence changes every note. Yet dark matter's greatest mystery isn't just what it does, it's what it is. Scientists have proposed everything from exotic, slow-moving particles to primordial black holes formed in the universe's first second. Some theories even suggest dark matter might interact with itself in ways we haven't yet detected, creating intricate substructures within galaxies. Every time we map the distortion of light around galaxy clusters, a phenomenon called gravitational lensing, or simulate the cosmos on supercomputers, the results point to dark matter's undeniable role, even as its true nature slips through our fingers. What's fascinating is how this enigma ties into the echoes of dying stars. When gravitational waves from a neutron star collision reach us, their journey has been shaped not just by visible galaxies, but by vast rivers of dark matter flowing between them. Future detectors might even use these waves to map the invisible cosmic web, turning stellar collapses into probes for the universe's hidden architecture. So while dark matter remains unseen, its influence is written into every chapter of the cosmos, from the birth of the first stars to the afterglow of the last supernova. It's the silent composer of the celestial symphony, ensuring that even in death, stars never truly fade into silence. The oldest starlight reaching our telescopes is more than just ancient, it's a time machine. When we capture photons that have journeyed for over 13 billion years, we're not just seeing distant stars, we're witnessing the universe's childhood, a time when galaxies were newborns and the cosmos was still learning how to shine. These primordial beams, stretched and reddened by the expansion of space itself, carry secrets about an era when the first stars flickered to life in a darkness unlike anything we know today. Those first stars weren't like the ones we see now, born from clouds of pure hydrogen and helium, the only elements available after the Big Bang. They were titans, hundreds of times more massive than our Sun. Without heavier elements to cool their cores, they burned ferociously hot and died young, exploding in supernovas so powerful they lit up the early universe like cosmic flashbulbs. Their deaths were the universe's first alchemy labs, spewing carbon, oxygen, and other vital elements into the void, seeding the cosmos with the ingredients for everything that would follow. But here's what's truly staggering. We can still detect the echoes of those explosions, faint traces of ultraviolet light absorbed by ancient gas clouds, leave shadows in the spectrum of even more distant quasars, bright beacons powered by supermassive black holes. These absorption lines are like cosmic barcodes, revealing the composition of the universe's first heavy elements. It's as if the stars left behind chemical fingerprints, telling us not just how they lived, but how their deaths transformed the cosmos from a simple soup of hydrogen into a rich, complex tapestry. And then there's the cosmic microwave background, the afterglow of the Big Bang itself. While not starlight, this faint radiation is the backdrop against which those first stars emerged. By studying its tiny fluctuations, scientists have mapped the seeds of structure in the early universe, the faint density variations that would one day collapse into stars and galaxies. It's like finding the blueprint for everything that exists today, hidden in the universe's oldest light. Yet the most profound revelation might be how fragile this ancient light is. The farther back we look, the scarcer these signals become, drowned out by the glare of younger stars or stretched into near invisibility by the expansion of space. Capturing them requires telescopes like Hubble's successor, the James Webb Space Telescope, designed to peer into the infrared, where these ancient photons, redshifted by their long journey, finally reveal themselves. Every new detection is a victory against time, a glimpse into an epoch when the universe was just beginning to write its story. So when astronomers point their instruments at these primordial beams, they're not just collecting data. They're assembling a family album for the cosmos, one that shows how the first stars lived, died, and in their passing, lit the way for everything that came after, including us. The space between stars might look like an endless void, but it's far from empty. Drifting through the vast expanses of our galaxy is a diffuse mixture of gas, dust, and energy we call the interstellar medium, and it holds the lingering traces of every star that ever lived and died. Picture it as the universe's attic, where cosmic keepsakes from ancient stellar explosions are carefully preserved. This isn't just floating debris, it's an active participant in the life cycle of the cosmos, a dynamic stage where the echoes of the past become the building blocks of the future. Most of this interstellar material exists as incredibly thin gas, about 1 atom per cubic centimeter on average. To put that in perspective, the air we breathe has about 25 quintillion molecules in the same space. But across light years of distance, these sparse atoms add up, forming massive clouds where new stars are born. The composition tells a story: about 70% hydrogen, 28% helium, and 2% heavier elements like carbon, oxygen, and iron, all forged in stellar furnaces and scattered by supernova. Every time a massive star explodes, it enriches this cosmic soup with new ingredients, gradually increasing the concentration of elements that can form planets and life. Then there's the dust. These microscopic grains, smaller than a wavelength of light, are made of silicon, carbon, and iron compounds, often coated in frozen water or carbon monoxide. While they make up only about 1% of the interstellar medium's mass, their effects are dramatic. They absorb and scatter starlight, creating the dark patches we see in the Milky Way, not empty holes, but dense curtains where dust blocks our view. Some of these grains are literal stardust, condensing in the outer atmospheres of aging stars before being blown into space. Others form in the shockwaves of supernova, where atoms bond together in the chaos of the explosion. But the interstellar medium isn't just passive material, it's alive with magnetic fields and turbulent motion. Charged particles spiral along these invisible field lines, while shock waves from stellar winds and supernova carve intricate bubbles and filaments into the gas. When we observe the aftermath of a star's death, like the Crab Nebula, we're seeing how its energy reshapes the surrounding medium, heating gas to millions of degrees and accelerating particles to near light speed. These processes create some of the most beautiful structures in the cosmos, glowing nebulae that shine in vivid reds and blues, illuminated by the radiation of nearby stars. What's truly remarkable is how this medium preserves information. Just as tree rings record Earth's climate history, the interstellar medium holds chemical signatures of stellar evolution. By analyzing the absorption lines in starlight that passes through these clouds, astronomers can read the composition of gas across the galaxy, identifying elements from stars that died billions of years ago. Some clouds even contain molecules like ethanol or formaldehyde, complex chemistry written in the language of space itself. So when we look at the dark spaces between stars, we're not seeing emptiness. We're seeing a living archive, a constantly changing canvas where the past and future of the cosmos intertwine. Every atom, every dust grain, every ripple in the magnetic field is a note in the grand symphony of stellar life and death, a song that began with the first stars and continues to play around us even now. For centuries, astronomers relied on just one cosmic messenger, light, to decode the universe's secrets. But now, we're entering an era where we can sense the cosmos in entirely new ways, combining the whispers of gravitational waves with the shouts of gamma rays and even the ghostly trails of neutrinos. This multi-messenger astronomy is like suddenly gaining new senses after a lifetime of seeing in black and white. When a massive star collapses or neutron stars collide, it doesn't just send out light, it broadcasts its story across multiple channels, each revealing a different piece of the puzzle. Take the historic event of August 17, 2017. Gravitational wave detectors picked up the unmistakable ripple of two neutron stars spiraling together 130 million light-years away. Just 2 seconds later, space telescopes caught a gamma ray burst from the same patch of sky, a brilliant flash signaling the moment those dense stellar corpses merged. Within hours, observatories around the world turned their gaze to that point, capturing ultraviolet, optical, and infrared light that painted a vivid picture of the aftermath. For the first time, we weren't just reading about cosmic collisions in textbooks. We were watching one unfold in real time, through every available lens. The power of this approach lies in how each messenger fills gaps the others leave. Gravitational waves tell us about the masses and spins of colliding objects, but they can't pinpoint locations precisely. Light reveals exact positions and chemical compositions, but gets obscured by dust or drowned in brighter sources. Neutrinos, nearly massless particles that streak through matter like phantoms, carry information straight from a collapsing star's core, where even X-rays can't escape. Together, they form a complete narrative, like witnesses describing the same event from different angles. Consider what happened when Supernova 1987 exploded in the Large Magellanic Cloud. Light took hours to brighten enough for telescopes to notice, but neutrino detectors registered a burst of 20 particles minutes earlier, the first alert that a star's core had just collapsed. Those neutrinos gave us a front-row seat to physics no telescope could see, confirming theories about how shockwaves rip through dying stars. Today, with more sensitive detectors, we can catch these signals from much farther away, turning random cosmic explosions into coordinated global observing campaigns. The future of this field is even more exciting. Next-generation gravitational wave observatories will detect fainter ripples from deeper space, while neutrino telescopes grow larger and more precise. Automated alert systems now scan the skies constantly, ready to swing telescopes toward new events within seconds. Somewhere out there right now, another neutron star collision or supernova is brewing, and when it happens, we'll be listening, watching, and sensing it in ways that would have seemed like magic just a generation ago. This isn't just about collecting more data. It's about rewriting our understanding of the universe's most violent events. Every time we combine these cosmic messengers, we're assembling a Rosetta Stone for stellar death, translating the universe's most dramatic moments into a language we can finally understand. Long before telescopes or modern science, ancient skywatchers recorded sudden, brilliant lights flaring where no star had shone before. These celestial apparitions, now recognized as supernova, were so startling they became etched into human history. One of the most famous erupted in the year 1054, when Chinese astronomers documented a guest star so bright it was visible in daylight for 23 days. Its remnant, the Crab Nebula, still glows today, a tangled web of gas and dust expanding at nearly 1,000 miles per second. But this wasn't just a spectacle, it was a cosmic timestamp, allowing modern astronomers to calculate the explosion's exact age and trace how its debris has evolved over nearly a millennium. Halfway around the world, indigenous rock art in the American Southwest may depict that same event, with a crescent moon drawn beside a radiant circle, matching the supernova's position near the moon in July of that year. Meanwhile, in Japan, court poets described the sudden star as an omen, its brilliance fading over months until it vanished entirely. These scattered accounts, once thought to be myths, now serve as critical data points. By comparing historical descriptions of brightness and duration with modern supernova models, scientists can reconstruct the explosion's type, energy, and even the elements it scattered into space. But the 1054 event wasn't alone. Korean records mention an even earlier, bushy star in the year 1080, likely the supernova that left behind the faint remnant known as G 320.4-1.2. And in the southern hemisphere, Aboriginal Australian oral traditions speak of a bright new star that appeared near the constellation Crux, possibly referencing the Vela supernova, whose ghostly filaments still shimmer 12,000 years after the explosion. What makes these ancient observations invaluable isn't just their rarity, it's their precision. Before the invention of clocks or standardized calendars, astronomers tracked celestial events by lunar cycles and planetary positions. When a Chinese scribe noted the 1054 supernova's position near the constellation Taurus, they provided coordinates modern telescopes could use to pinpoint its remnant. Similarly, Islamic scholars in the Middle Ages recorded the supernova of the year 1006 with such detail. We now know it was a Type Ia explosion, a white dwarf detonating in a binary system. These historical supernovae do more than satisfy curiosity. They help calibrate the cosmos. By studying how their remnants expand over centuries, astronomers refine models of stellar death. The Crab Nebula's pulsar, spinning 30 times per second, confirms how neutron stars form in supernova blasts. The faint X-rays from G 320.4-1.2 reveal how heavy elements disperse into interstellar space. Even the absence of records is telling when no bright supernova appear in European chronicles for 600 years. It hints at how dust in our galaxy's spiral arms might have obscured them. So when we read these ancient accounts, we're not just uncovering the past. We're collaborating with observers who lived 1,000 years ago, their careful notes still guiding our exploration of the stars. Their guest stars were more than omens. They were the first chapters in humanity's growing understanding of the universe's violent, beautiful transformations. A supernova remnant is the universe's way of turning destruction into art, a celestial phoenix rising from its own ashes. Take the Crab Nebula, that magnificent swirl of gas and dust stretching 6 light-years across. What we're seeing isn't chaos, but a carefully preserved crime scene from the year 1054, when a massive star met its explosive end. The intricate filaments aren't random, they're shockwaves frozen in time, expanding at nearly 1,000 miles per second, while glowing with the energy of the pulsar at their heart. This is stellar archaeology at its finest, where every twisted ribbon of gas tells part of the story. The colors alone reveal secrets invisible to the naked eye. Those vivid red tendrils, they're hydrogen gas, excited by radiation from the central neutron star. The blue haze comes from electrons spiraling along magnetic fields at nearly the speed of light. And that eerie green tint, that's oxygen doubly ionized by the pulsar's fierce winds. Together, they form a cosmic fingerprint, showing exactly which elements the dying star fused during its life and in its final cataclysm. Modern telescopes can even map how these elements are distributed, revealing how the explosion ejected different materials in specific directions, like a chef carefully layering ingredients in a celestial soufflé. But the Crab is just one example in a gallery of stellar destruction. The Veil Nebula in Cygnus paints a different picture, delicate lacework stretching over 100 light-years, the remnants of a star that exploded 20 times more violently than the Crab's progenitor. Its intricate structure shows how shock waves interact with interstellar gas, creating ripple patterns similar to those in a pond, but on an unimaginable scale. Then there's Cassiopeia A, whose light reached Earth around the year 1680, though no one recorded seeing it, perhaps obscured by cosmic dust. Today, its remnant glows in X-rays, revealing titanium and chromium blasted outward at millions of miles per hour, elements normally buried deep in a star's core. What makes these remnants so valuable isn't just their beauty, it's their lifespan. While the supernova itself may shine brighter than a galaxy for weeks, its remnant persists for millennia, evolving in ways that let us study stellar death in slow motion. The youngest remnants, like G 1.9 plus 0.3 in our galaxy, which exploded just about 150 years ago, show raw, unfiltered violence, their shockwaves still plowing through surrounding gas at 10% the speed of light. Older ones, like the Vela supernova remnant, estimated at 11,000 years, have softened into vast, wispy structures where the original explosion's energy has largely dissipated into heating interstellar space. Perhaps most remarkably, these glowing graves are cosmic recycling centers. As they expand, they sweep up surrounding gas and dust, compressing it until new stars can form. The heavy elements forged in the supernova, oxygen, carbon, iron, become part of future planets and ultimately life. When we look at the Crab Nebula's pulsing heart or the Veil's delicate filaments, we're not just seeing a dead star, we're witnessing the delivery of raw materials that might one day form mountains, oceans, or even living cells in some distant solar system. The next time you see an image of these breathtaking remnants, remember, you're not looking at an ending. You're seeing the universe's most spectacular reinvention, where death gives birth to new possibilities, and every explosion writes its legacy across the cosmos in light and elements that will endure for millions of years. Gamma-ray bursts are the universe's flashbulbs, blindingly bright, vanishingly brief, and capable of outshining entire galaxies for the few seconds they last. These cosmic fireworks aren't just random flashes, they're the death cries of the most massive stars or the collision of neutron stars, events so violent they birth black holes in their wake. When astronomers first detected these bursts in the 1960s, they seemed like military secrets, brief, mysterious blips picked up by satellites designed to monitor nuclear tests. It took decades to realize we were witnessing the most energetic explosions since the Big Bang itself. What makes these bursts so astonishing is their raw power. In just a few seconds, a single gamma-ray burst can release more energy than our sun will emit in its entire 10 billion-year lifetime. That energy isn't spread evenly, it's focused into narrow beams like cosmic laser pointers sweeping across the universe. If one of those beams happened to point directly at Earth, we'd detect it billions of light years away. But here's the twist: for every burst we see, there are hundreds more pointing in other directions, invisible to us. It's like watching lightning from a distant storm. We only notice the bolts that happen to strike our line of sight. These bursts come in two distinct flavors, each telling a different story of stellar demise. The long bursts, lasting more than 2 seconds, are the final acts of massive stars collapsing into black holes. As the star's core implodes, jets of plasma erupt from its poles at nearly the speed of light, punching through the star's outer layers and blasting into space. These jets are so focused and energetic, they produce gamma rays, the most powerful form of light, as they collide with surrounding gas. The shorter bursts, lasting less than 2 seconds, are thought to come from neutron star collisions, where two ultra-dense remnants spiral together in a final embrace, merging into a black hole in a spectacular kilonova explosion. But gamma rays are just the opening act. As the jet plows through interstellar gas, it creates an afterglow, a fading cascade of X-rays, visible light, and radio waves that can last for weeks. This afterglow is like the smoke after a cannon shot, allowing astronomers to pinpoint the burst's origin and study its environment. In 2017, when detectors caught both gravitational waves and a gamma-ray burst from the same neutron star collision, it confirmed a decades-old theory and opened a new window into how heavy elements like gold and platinum are forged in these cosmic furnaces. What's truly humbling is how these fleeting flashes connect us to the universe's most extreme physics. The jets in gamma-ray bursts are nature's particle accelerators, far more powerful than anything we could build on Earth. They're laboratories for testing Einstein's theory of relativity, where matter moves so close to light speed that time dilation becomes measurable. Some bursts even carry clues about the early universe. Their light, stretched by cosmic expansion during its billion-year journey, acts as a probe for the gas clouds between galaxies. So while these bursts last mere moments, their legacy endures. They're not just explosions, they're cosmic signposts, marking the violent births of black holes and the creation of elements that will one day form new stars, planets, and perhaps even life. Every time a satellite detects one of these distant flashes, we're witnessing the universe at its most raw and unfiltered, a reminder of how dynamic, destructive, and dazzlingly creative the cosmos truly is. Of all the cosmic collisions, few are as dazzling or as lucrative as the merger of two neutron stars. When these ultra-dense remnants spiral together in a final, fatal dance, they don't just create gravitational waves, they unleash a kilonova, an explosion so powerful it forges the universe's heaviest elements in a single, spectacular burst. Picture two city-sized objects, each packing more mass than our sun, smashing together at nearly the speed of light. The impact is so violent, it rips neutron-rich material from their surfaces, flinging it into space where atomic nuclei rapidly assemble into gold, platinum, uranium, and other precious metals. In seconds, this cosmic alchemy produces enough gold to outweigh entire planets, scattering treasure across the cosmos that will one day become part of asteroids, Earth's crust, and even the jewelry we wear. What makes kilonovae so special isn't just their brilliance, it's their distinct, glowing signature. Unlike supernova, which shine for weeks, kilonovae fade within days, their light tinged red from the radioactive decay of freshly minted heavy elements. This unique color comes from lanthanide's rare earth elements with complex atomic structures that absorb and re-emit light in very specific ways. When astronomers first spotted this telltale glow accompanying the gravitational waves from a neutron star collision in 2017, it confirmed a decades-old theory. These mergers are the universe's primary foundries for elements heavier than iron. The aftermath of a kilonova is just as fascinating as the explosion itself. The ejected material expands in a lopsided cloud, shaped by the intense magnetic fields and rapid spins of the original neutron stars. Some gets heated to billions of degrees, emitting X-rays and gamma rays, while cooler clumps form dust grains that will eventually seed future generations of stars and planets. And buried in that debris might be the strangest relics of all, specks of super-heavy elements that don't exist naturally on Earth, forged under conditions so extreme they push the limits of atomic stability. But kilonovae aren't just cosmic jewelry shops, they're also vital laboratories for physics we can't replicate on Earth. The densities inside colliding neutron stars approach those of an atomic nucleus, letting scientists study how matter behaves under pressures so intense protons and electrons merge into neutrons. The explosions also test Einstein's theories in extreme gravity, while their jets narrow beams of particles moving at 99.9% the speed of light, show how nature accelerates matter to energies far beyond our most powerful particle colliders. Perhaps most remarkably, these collisions bridge the gap between the very large and the very small. The gravitational waves they produce reveal the stars' masses and orbits, while the light from their explosions exposes the quantum processes building atomic nuclei. It's as if the universe handed us a Rosetta Stone, translating between the language of gravity and the language of chemistry. And with every new kilonova detected, we're decoding more of its secrets, one glittering, radioactive echo at a time. The universe isn't silent, it's a concert hall of collapsing stars, black hole mergers, and spinning neutron stars, all vibrating the fabric of spacetime itself. But until recently, these cosmic vibrations were hidden from us, detectable only as squiggles on a scientist's graph. That changed when researchers began translating gravitational wave data into sound, giving humanity its first chance to hear the cosmos. The result, a haunting collection of chirps, thuds, and hums, each one the fingerprint of a violent event millions or even billions of light years away. Take the first gravitational wave ever detected, the merger of two black holes back in 2015. When sped up and converted to audio, it sounds like a quick whoop, a fleeting blip that represents the final moments of a dance that lasted billions of years. As the black holes spiraled closer, their gravitational waves increased in pitch and volume like a cosmic slide whistle until the moment they collided. That final chirp is the sound of 30 solar masses converting into pure energy in a fraction of a second, rippling outward at the speed of light. What's astonishing isn't just the sound itself, it's how much information is packed into that brief noise. The pitch reveals the black hole's masses, the timing tells us their distance, and the shape of the waveform hints at how fast they were spinning before impact. But not all cosmic sounds are so abrupt. When neutron stars collide, they produce a richer, more complex tone, a sort of glissando that rises in pitch before culminating in a bright, metallic ring. That's followed by a softer afterglow of higher frequencies, the audible signature of debris swirling into a newly formed black hole or hypermassive neutron star. These collisions aren't just sonically distinct, they are also chemical factories. The same event that produces that eerie sound also forges enough gold and platinum to outweigh entire planets, scattering precious metals across the cosmos. Some of the most haunting sounds come from solitary pulsars spinning neutron stars that beam radiation like cosmic lighthouses. Their steady pulses, when converted to audio, become rhythmic clicks or even musical beats, some as precise as atomic clocks. The Crab Nebula's pulsar, for instance, produces a sharp tap 30 times per second, a metronome ticking away inside the wreckage of a star that exploded 1,000 years ago. Other pulsars wobble slightly as they spin, creating a warble in their tone that reveals the presence of unseen planets or companion stars tugging on them. What makes these sounds so powerful is how they connect us to the universe on a visceral level. Light from distant stars takes years to reach us, but gravitational waves are the event. They carry the actual vibrations of cosmic collisions directly to our detectors. Hearing them transforms abstract astrophysics into something immediate and almost intimate, like listening to a heartbeat from across the galaxy. Scientists are now using these sounds to search for patterns we might miss in visual data, like the faint whisper of a small black hole merging with a neutron star, or the background hum of countless unresolved collisions from the early universe. So the next time you look up at the night sky, remember, it's not just a silent panorama of pinprick lights. It's a dynamic, vibrating arena where stars live, die, and collide, and for the first time in history, we can hear their stories as they unfold. The gravitational waves we detect today are just the first notes in a cosmic symphony we're only beginning to hear. Current observatories like LIGO and Virgo have opened our ears to collisions of black holes and neutron stars, but they're limited to catching the universe's loudest, lowest frequency events, like hearing only the bass drums in an orchestra. That's about to change. A new generation of detectors poised to launch in the coming decades will tune into frequencies we've never accessed before, revealing a richer, more nuanced soundtrack of the cosmos. At the forefront is the Laser Interferometer Space Antenna, or LISA, a revolutionary mission led by the European Space Agency with NASA, a partnership. Unlike ground-based detectors, LISA will consist of 3 spacecraft flying in a precise triangular formation, 2.5 million kilometers apart, connected by laser beams. Free from Earth's seismic noise and with arms thousands of times longer than LIGO, this space-based observatory will detect gravitational waves at frequencies 1 million times lower than current instruments can sense. Imagine switching from a telescope that only sees fireworks to one that captures the slow dance of galaxies. That's the leap LISA represents. What makes this so transformative? Lower frequency waves carry stories from entirely new cosmic sources. LISA could hear the gentle spirals of supermassive black holes merging at the hearts of distant galaxies, events so colossal they shake spacetime for years. It might catch the rhythmic hum of white dwarf binaries, pairs of dead stars whirling around each other in a slow, steady waltz that's been going on for millennia. There's even the tantalizing possibility of detecting primordial gravitational waves, ripples from the Big Bang itself frozen into the fabric of the universe. These signals would be like uncovering sheet music from the universe's first moments, a direct window into physics far beyond what particle colliders can probe. But LISA isn't the only upcoming ear trained on the cosmos. Earth-based detectors are advancing too. the Einstein telescope planned beneath Europe and Cosmic Explorer, a proposed U.S. observatory, will be 10 times more sensitive than current instruments. Buried deep underground to minimize interference, they'll catch fainter neutron star collisions farther back in time, potentially hearing the very first stellar deaths in the universe. Meanwhile, pulsar timing arrays networks of radio telescopes tracking the ultra-regular flashes of spinning neutron stars are already hinting at a background hum of gravitational waves from countless supermassive black hole mergers across cosmic history. The future of gravitational wave astronomy isn't just about more detections. It's about layering these observations into a fuller picture. Imagine combining LISA low-frequency hum with LIGO sharp chirps and pulsar timing steady beat, much like blending instruments in an orchestra. Together, they'll reveal how black holes grow over cosmic time, how galaxies merge, and perhaps even exotic objects we've yet to imagine, like cosmic strings, hypothetical defects in spacetime left over from the universe's birth. Every time we've built a better gravitational wave detector, the universe has surprised us. The first merger detection in 2015 upended our understanding of how common black holes are. The neutron star collision in 2017 showed us where heavy elements are forged. With these new observatories, we're not just turning up the volume, we're unlocking entirely new channels in the cosmic soundtrack, ready to hear whatever secrets the universe whispers next. Quantum mechanics and gravity have always been the universe's most reluctant dance partners, one ruling the realm of atoms, the other governing stars and galaxies. Yet near black holes, where gravity warps spacetime to its extremes, these two titans might finally reveal how they intertwine. Hidden in the faint ripples of gravitational waves could be quantum whispers, subtle distortions that betray the fabric of reality at its smallest scales. Imagine listening to a recording of a symphony and hearing, beneath the cellos and violins, the faint hum of individual strings vibrating. That's what scientists hope to detect in gravitational wave signals, the microscopic tremors where spacetime itself might be quantized. These quantum echoes could arise from the event horizon's edge, a boundary so paradoxical, it bends the rules of both relativity and quantum theory. According to some models, when matter falls into a black hole, quantum fluctuations near the horizon might imprint faint oscillations onto outgoing gravitational waves. It's like tossing a pebble into a pond and noticing tiny, secondary ripples superimposed on the larger waves, an effect so subtle current detectors can't yet spot it. But future observatories like the proposed Einstein telescope or space-based LISA could be sensitive enough to catch these fingerprints. If they do, it would be the first experimental evidence that gravity, like the other fundamental forces, has a quantum nature. The implications are staggering. If quantum gravity leaves traces in gravitational waves, we might finally bridge the century-old gap between Einstein's relativity and quantum mechanics. Some theories, like loop quantum gravity, predict spacetime itself has a granular structure at tiny scales. Think of it as the universe's pixels. Others, like string theory, suggest extra dimensions could subtly alter how gravitational waves propagate. Each hypothesis leaves a distinct signature in the wave's shape and frequency, like dialects in a cosmic language. Detecting these nuances wouldn't just confirm quantum gravity, it could tell us which version of the theory matches reality. Already, researchers are simulating what these quantum echoes might look like. One provocative idea comes from firewall theories, which suggest the event horizon isn't the smooth gateway relativity predicts, but a seething wall of high-energy particles. A black hole merger involving such a firewall would produce gravitational waves with telltale high-frequency bumps in the signal, Another clue might hide in how black hole ringdowns, the fading vibrations after a collision, deviate from classical predictions. Quantum corrections could make these aftertones decay slightly faster or slower, like a bell whose chime is subtly altered by unseen cracks. What makes this search so thrilling is its unpredictability. Quantum gravity's effects might not match any existing model. They could reveal entirely new physics. Just as the first gravitational wave detection upended our understanding of black hole populations, quantum echoes might expose phenomena we haven't even imagined. Perhaps spacetime isn't smooth but fractal, or maybe black holes leak information in ways that subtly modify their gravitational wave emissions. Every new waveform analyzed is a potential Rosetta Stone, waiting to decode the universe's deepest laws. So while today's detectors listen for the thunderous crashes of black holes, tomorrow's could be tuning into the quantum murmurs beneath. It's a hunt for the universe's quietest secrets, hidden in plain sight within the very waves that already transformed astronomy. And if we succeed, the echoes of collapsing stars might finally reveal how spacetime itself is woven together at the smallest scales. Einstein's theory of relativity holds an eerie prediction: time doesn't tick at the same rate everywhere in the universe. Near a collapsing star where gravity twists spacetime into knots, clocks would crawl compared to those on Earth. This phenomenon, called time dilation, means the echoes we detect from these cataclysmic events aren't just faint, they're stretched and warped, like a record played at the wrong speed. Imagine watching a fireworks display through a funhouse mirror. The colors and shapes are still there, but distorted in ways that challenge your perception. That's the puzzle astronomers face when interpreting signals from neutron star collisions or black hole births. The closer you get to a massive object, the stronger this time-slowing effect becomes. Near a neutron star's surface, where gravity is billions of times stronger than Earth's, time passes about 30% slower. For a black hole's event horizon, it grinds to a near halt from an outsider's perspective. This distortion doesn't just affect the star's final moments, it alters how we perceive the entire aftermath. Gravitational waves from a merger might arrive stretched out, their frequencies shifted lower, while light from the explosion could appear redder and dimmer than expected. It's as if the universe itself is applying a cosmic filter to these events, forcing us to decode the true timeline beneath the distortion. This time-warping effect creates fascinating challenges and opportunities for astrophysicists. When LIGO detects a gravitational wave signal, scientists must account for how the immense gravity of the source stretched time during the collision. A black hole merger that lasted seconds in its own reference frame might appear drawn out over minutes in our data. Similarly, the afterglow of a kilonova could seem to fade slower than it actually does, like a slow-motion replay of a supernova. Untangling these effects requires precise mathematical modeling, essentially reverse engineering Einstein's equations to reconstruct the event's true timescale. But time dilation isn't just an obstacle, it's also a tool. By measuring how much a signal is stretched, astronomers can estimate the mass of the collapsing object. A particularly distorted gravitational wave might reveal a previously unseen class of black holes, while subtle timing shifts in pulsar flashes could hint at hidden companions warping spacetime nearby. Some researchers even speculate that extreme time dilation near supermassive black holes might preserve information about the early universe, like a cosmic time capsule frozen in the gravitational deep freeze. What's most mind-bending is how this connects to our daily lives. The GPS in your phone already corrects for time dilation. Satellites orbiting Earth experience time slightly faster than we do on the surface, and without adjusting for this, navigation would drift by kilometers within hours. On a cosmic scale, these effects are magnified exponentially. The echoes of collapsing stars don't just carry information about their origins, they're encrypted with the very fabric of spacetime itself, a reminder that gravity doesn't just shape the universe. It dictates how we perceive its story. The silence of the cosmos is one of its greatest mysteries. With billions of galaxies, each containing billions of stars, the universe should be teeming with civilizations, yet we've heard nothing. This eerie quiet is known as the Fermi paradox, and it forces us to confront a haunting question. If intelligent life is out there, why haven't we found even a whisper of its existence? One provocative theory suggests we might be looking and listening in the wrong way. Advanced civilizations wouldn't just broadcast radio signals. They might manipulate the fabric of spacetime itself, leaving fingerprints in the very echoes of dying stars. Think about how humanity's energy needs have evolved. We started with fire, then harnessed steam, then split the atom. A civilization thousands or millions of years ahead of us wouldn't be tinkering with fossil fuels or even nuclear fission. They'd be tapping into cosmic power sources beyond our imagination. One such source, the unimaginable energy released when stars collapse into black holes or neutron stars. The gravitational waves from these events carry more energy than all the stars in a galaxy emit in years, a concentrated burst just waiting to be harnessed. This idea isn't pure speculation. Physicists like Freeman Dyson once proposed that advanced civilizations might build megastructures around stars to capture their energy. But why stop at starlight when you could harvest the far more intense energy of a supernova or a merging black hole? Theoretically, a sufficiently advanced species could redirect collapsing stars into precise collisions, creating controlled gravitational wave factories that generate clean, nearly limitless power. These engineered mergers would leave subtle but detectable anomalies in their signals, perhaps an unusual symmetry in the gravitational waves, or mergers happening in empty space far from any galaxy where natural collisions would be rare. Scientists are already scanning gravitational wave data for irregularities that might hint at intelligence at work. Some patterns, like black holes merging at impossible speeds or neutron stars colliding in suspiciously perfect orbits, could be cosmic red flags. Even stranger are the hypothetical Dyson spheres built around pulsars, structures that would modulate the star's beams into deliberate patterns, turning these natural lighthouses into galactic telegraphs. Yet if such civilizations exist, their silence raises another chilling possibility. Harnessing the energy of dying stars might be the last act of a civilization before its demise, a final, desperate gamble to survive. Or perhaps they've moved beyond physical forms entirely, uploading their consciousness into quantum substrates where gravitational waves are their natural medium of communication, speaking in a language we're only beginning to perceive. The universe's silence might not be emptiness at all. It could be a symphony playing in a key we haven't learned to hear, one written not in radio waves or light, but in the ripples of spacetime itself. Every black hole collision we detect could be more than a natural disaster. It might be a signature, a monument, or even a message. And if that's true, then the real question isn't why we haven't heard from alien civilizations. It's whether we're listening closely enough to the right cosmic echoes. The universe has always been the ultimate muse, its celestial dramas written in light and gravity, translated through human hands into symphonies, paintings, and poetry. Long before telescopes revealed the physics of supernova or gravitational waves, artists sensed the cosmos's grandeur, channeling its mysteries into works that resonate with the same awe we feel today. Take composer Gustav Holst's The Planets, written in 1916, a swirling orchestral journey that captures Mars's warlike fury and Neptune's eerie tranquility. Though Holst knew nothing of modern astrophysics, His music somehow mirrors the violent beauty of planetary formation, the way gravity sculpts worlds from chaos. Visual artists, too, have turned cosmic violence into transcendent beauty. The swirling golds and blues of Vincent van Gogh's Starry Night evoke not just a quiet village but the churning dynamism of the universe itself, an intuition confirmed centuries later when astronomers discovered turbulent magnetic fields shaping nebulae. Japanese artist Hokusai, famed for the Great Wave, once painted a supernova in 1835, its radiant spikes mirroring the Crab Nebula's actual structure, though he'd never seen it through a telescope. These creators weren't just imagining, they were channeling patterns the universe repeats at every scale, from brushstrokes to supernova remnants. Today, science and art collaborate more explicitly. Data sonification projects transform gravitational waves into audible chords. The merger of two black holes becomes a rising whoop. Neutron stars a metallic chime. Installations like Pulsar by artist Lillian Layen pulse with light timed to actual neutron star frequencies, while composers like John Luther Adams craft entire scores from astrophysical data, letting the universe dictate the notes. Even NASA joins in, assigning musicians to play telescope data, turning the infrared glow of distant galaxies into haunting piano melodies. Literature, too, bends toward these echoes. Poet Tracy K. Smith's Life on Mars weaves cosmic imagery with human longing, while sci-fi authors like Lou Sixon imagine civilizations manipulating gravity itself. These works don't just describe the cosmos, they ask why its mysteries move us so deeply. Perhaps it's because stellar echoes mirror human experiences, creation, destruction, and the fragile persistence of memory. A supernova's afterglow isn't so different from a painting hanging in a museum centuries after the artist's death. Both are whispers across time, proof that beauty survives its makers. The most profound collaborations happen when artists and scientists sit side by side. When LIGO detected its first gravitational waves, choreographer Adrian M.Claire created a dance where performers became colliding black holes, their movements tracing the signal's waveform. In that moment, abstraction became visceral, the universe's music made flesh. Whether through pigment, sound, or motion, art reminds us that the cosmos isn't just equations and data. It's a story we're all part of, written in starlight and spacetime, waiting for the next interpreter to give it voice. There's something profoundly humbling about standing beneath a starry sky and realizing the light you see is a delayed broadcast. Some of those stars have been dead for millennia, their final gasps still traveling toward us. These cosmic echoes do more than illuminate the physics of stellar collapse. They hold up a mirror to our own impermanence. Every supernova remnant, every ripple in space-time whispers the same truth: nothing in the universe is static. The same forces that tear stars apart also sculpt galaxies, shape planets, and eventually reclaim all things. We're transient witnesses to a cosmic cycle far grander than human history, let alone a single lifetime. This realization sparks questions that have haunted philosophers since antiquity. If a star's death can reverberate for billions of years, what legacy do our brief lives leave? The carbon in our bodies, forged in stellar furnaces, connects us to these ancient cycles, yet our consciousness allows us to contemplate them, a paradox both beautiful and unsettling. Astronomer Carl Sagan captured this duality when he wrote that we are a way for the cosmos to know itself, suggesting our fleeting existence might hold meaning precisely because we can perceive the universe's grandeur. Time takes on new dimensions when measured against stellar echoes. Human civilizations rise and fall in mere millennia, a blink compared to the Crab Nebula's 1,000-year expansion or the billion-year journeys of gravitational waves. Yet without conscious observers to trace these phenomena, would the universe's story still matter? This tension between cosmic scale and human significance lies at the heart of existential thought. Some find it terrifying, the idea that we're inconsequential stardust adrift in an indifferent void. Others see liberation in accepting our smallness, recognizing that our brief spark of awareness lets us participate in something eternal. Perhaps the deepest lesson lies in how these echoes reframe mortality. Just as a supernova's debris seeds new stars, our actions ripple through time in ways we can't predict. The light from long-dead stars still guides sailors. The gold in ancient treasures came from neutron star collisions predating Earth itself. Nothing truly vanishes, it transforms. Whether through art, discovery, or simple kindness, we contribute to a tapestry far larger than ourselves. The universe forgets nothing. Every gravitational wave, every photon from a dying star, is proof that even endings propagate forward, shaping whatever comes next. So while the cosmos may dwarf our individual existence, it also offers a strange comfort. We're woven into its fabric, participants in an unbroken chain stretching from the first stars to whatever wonders lie ahead. The echoes we leave, whether literal or metaphorical, are ours to choose. The universe's grand mysteries aren't just for professional astronomers in high-tech observatories. They're waiting for you, right now, from your backyard or living room. Thanks to the explosion of citizen science projects, anyone with curiosity and an internet connection can help decode the echoes of collapsing stars, supernova, and even distant galaxy mergers. Platforms like Zooniverse have turned cosmic discovery into a global team sport, where teachers, artists, and retirees regularly spot celestial phenomena that supercomputers miss. It's a revolution in how science happens, proving that the most powerful tool in astronomy isn't just a telescope, it's the human brain's knack for pattern recognition. Take the case of supernova hunters. Every night, automated telescopes scan the skies, capturing thousands of images of galaxies. But computers struggle to distinguish a new supernova, a star's final flash, from camera glitches or asteroids. That's where volunteers step in. Projects like Supernova Hunters on Zooniverse train everyday people to scan these images, flagging potential explosions. In 2020 alone, amateur participants identified over a dozen previously unknown supernova, some in galaxies millions of light-years away. These discoveries aren't just novelties. They help professionals prioritize which events to study with limited telescope time, turning random stargazers into critical links in the scientific chain. Then there's Gravity Spy. When LIGO detects gravitational waves, the signal is often buried in noise glitches from earthquakes, passing trucks, or even the detector's own machinery. Citizen scientists classify these disturbances by their shapes, teaching AI systems to filter them out. One volunteer, a retired nurse with no physics background, became so skilled at recognizing wave patterns that she co-authored a peer-reviewed paper on gravitational wave glitches. It's a perfect example of how collective human intuition can refine even the most advanced technology. But perhaps the most astonishing contributions come from projects like Radio Galaxy Zoo, where volunteers trace the jets of supermassive black holes across radio and infrared images. In 2018, a Dutch schoolteacher noticed an unusual alignment of jets spanning millions of light-years, a structure so bizarre. It led to the discovery of a previously unknown class of black hole behavior. Professional astronomers had overlooked it for years, buried in petabytes of data. This is the magic of citizen science, fresh eyes seeing what experts assumed wasn't there. What makes these efforts so transformative isn't just the discoveries, it's how they redefine who gets to participate in science. A teenager in Nairobi can classify galaxy shapes for the Galaxy Zoo project, while a farmer in Nebraska scans telescope data for pulsars through Einstein at Home. These platforms don't just crowdsource labor, they democratize wonder, letting people touch the cosmos in ways once reserved for PhDs. And sometimes that connection sparks lifelong journeys. Multiple professional astronomers today began as Zooniverse volunteers, their curiosity ignited by spotting a supernova or exoplanet from their home computers. The next cosmic revelation might not come from a multi-million-dollar observatory, but from someone scrolling through telescope images on their lunch break. Every time a volunteer tags a distant supernova or filters a gravitational wave glitch, they're adding another note to humanity's growing symphony of cosmic understanding, proof that the universe's echoes aren't just for scientists to interpret, but for all of us to share. Hollywood loves painting black holes as insatiable monsters, sucking everything into their inescapable gullets, but the truth is far more intriguing. While their gravity is undeniably powerful, black holes don't indiscriminately vacuum up the cosmos like some interstellar Hoover. In fact, their gravitational influence behaves much like any other massive object until you cross the point of no return. Take our own solar system. If the sun magically collapsed into a black hole of the same mass tomorrow, Earth's orbit wouldn't change. We'd still follow the same elliptical path, just in eternal darkness. The real magic happens in the extreme environment near the event horizon, where gravity warps spacetime so severely that even light can't escape. This misconception overshadows black holes' most fascinating feature, their dynamism. Far from being static pits, they're active participants in cosmic evolution. Supermassive black holes at galactic centers, for instance, regulate star formation like cosmic thermostats. Their gravitational tides can shred gas clouds, preventing new stars from forming too quickly, while their jet streams of plasma accelerated to near light speed, heat surrounding gas and sculpt entire galaxies. The Hubble Space Telescope has even captured black holes playing pinball with stars, flinging them across space like celestial billiard balls after close encounters. Perhaps the biggest myth is that black holes are silent. While no sound can escape them, their collisions send literal shockwaves through space-time gravitational waves that detectors like LIGO can translate into audible chirps. These ripples reveal black holes' spin rates, masses, and even how they formed. Some spin so fast, they distort space-time into a swirling vortex around them. Others, like the merging black holes detected in 2015, show how these objects can orbit each other hundreds of times per second before colliding in a burst of energy equivalent to converting 3 suns into pure gravitational waves. Even their darkness is misunderstood. While the event horizon itself emits nothing, the swirling accretion disks of superheated gas around many black holes outshine entire galaxies. Quasars, active black holes billions of times the sun's mass, are the universe's brightest persistent objects, visible across billions of light years. Some even act as cosmic lighthouses, their beams illuminating intergalactic gas like a flashlight in fog. The most poetic twist: black holes might not last forever. Quantum mechanics suggests they slowly evaporate over eons, leaking energy in the form of Hawking radiation. It's a reminder that even these cosmic titans are part of the universe's grand cycle, not eternal monsters, but transient phenomena that shape the cosmos before fading into the void like all things. Even our most advanced instruments face cosmic limits, like straining to hear a whisper across a roaring stadium. For every gravitational wave we detect, countless others slip through our nets, their signals too faint, too distant, or drowned out by the universe's background noise. Current detectors like LIGO are marvels of engineering, capable of measuring distortions 10,000 times smaller than a proton. yet they're effectively deaf to collisions involving black holes smaller than 5 solar masses or larger than 50. The quietest neutron star mergers, the faintest white dwarf dances. These events unfold in silence, their stories trapped beyond our reach. The challenge isn't just sensitivity, it's scale. Gravitational waves stretch and compress spacetime as they pass, but over interstellar distances, even cataclysmic events can leave only the subtlest imprint. A pair of merging black holes a billion light-years away might shift LIGO mirrors by less than the width of an atomic nucleus. Add interference from seismic tremors, passing trucks, or even quantum noise, the fundamental jitter of particles at the subatomic level, and the signal vanishes like a sigh in a hurricane. Even electromagnetic echoes face hurdles. Dust clouds absorb starlight, cosmic expansion redshifts signals into near invisibility, and the sheer time it takes light to cross the universe means some stellar deaths haven't reached us yet. But the next generation of observatories promises to push these boundaries. The Einstein telescope, planned for underground construction in Europe, will use cryogenically cooled mirrors and a triangular design to reduce noise, potentially detecting mergers 10 times farther away. Space-based detectors like LISA won't just evade Earth's vibrations. Their million-kilometer arms will tune into low-frequency waves from supermassive black holes, events so colossal they've been ringing through spacetime since before galaxies fully formed. Meanwhile, quantum squeezing techniques, which manipulate light at the subatomic level to reduce uncertainty, could sharpen our detectors' precision by 40%, revealing quieter collisions hidden in the data. The real game-changer might lie beyond hardware. Machine learning algorithms now sift through gravitational wave data like cosmic archaeologists, uncovering patterns too subtle for human analysts. In 2022, one such AI identified a previously missed neutron star merger buried in LIGO archives, a signal so weak it had been dismissed as noise. Other teams are training neural networks to reconstruct entire collision scenarios from partial data, like forensic artists sketching a crime scene from a single fingerprint. What's thrilling isn't just the prospect of hearing more. It's what these hidden echoes might reveal. Faint signals from the universe's first black holes could test whether they're primordial, born from density fluctuations in the Big Bang's aftermath. Undetected neutron star mergers might resolve the missing heavy elements problem, explaining why galaxies contain more gold than current models predict. And lurking in the noise could be entirely new phenomena: action clouds around black holes, cosmic strings vibrating from the early universe, or even anomalies that rewrite Einstein's relativity. The cosmos doesn't owe us clarity. Its whispers are fragmented, its signals scattered across billions of years. Yet with every technological leap, we're piecing together a fuller score of the stellar symphony, one where even the quietest notes hold universe-shaking secrets. Gravitational waves might be more than just cosmic vibrations. They could be the first faint whispers from realities beyond our own. The idea that ripples in spacetime carry traces of parallel universes sounds like science fiction, but it emerges from serious theoretical physics. According to string theory, our universe could be just one membrane or brain floating in a higher dimensional space, with other brains hovering nearby like invisible neighbors. When massive objects like black holes collide, their gravitational waves might leak into these extra dimensions, carrying subtle imprints of worlds we can't see. It's as if the universe's symphony is being played in a concert hall with hidden balconies. We hear the music, but faint echoes might reveal unseen listeners. One tantalizing clue could lie in how gravitational wave signals fade. In our familiar three-dimensional space, waves weaken predictably as they spread outward. But if some of their energy slips into extra dimensions, detectors might catch anomaly signals that dim faster than expected, like a voice losing volume in a maze of unseen corridors. Researchers have already scoured LIGO data for these discrepancies, though no smoking gun has emerged yet. Another hint might hide in high-frequency gravitational waves, which current detectors can't sense. Future observatories tuned to these frequencies could uncover harmonic overtones in the cosmic symphony, vibrations that don't fit our universe's known physics, potentially pointing to interactions with other brains. The wildest possibility that some black holes aren't products of collapsed stars at all, but primordial knots of spacetime formed during collisions between our brain and another. These brain-world black holes would have distinct mass and spin signatures, their gravitational waves ringing with frequencies that betray their extraterrestrial origins. While speculative, the search for these outliers is already reshaping how scientists analyze merger data, treating every signal as a potential cosmic cipher waiting to be cracked. Of course, the multiverse remains fiercely debated. Critics argue that without direct evidence, these ideas are more philosophy than physics. But gravitational wave astronomy is young, and every new detection adds another day to point to the mystery. Whether extra dimensions exist or not, the pursuit itself has already expanded our imagination of what's possible, turning the cosmos from a static stage into a dynamic, multi-layered puzzle. The next time a gravitational wave chirps through our detectors, it might not just be telling the story of colliding black holes. It could be carrying a message from a reality we've yet to dream of. The stars may not belong to anyone, but the knowledge we extract from their echoes certainly raises profound ethical questions. When telescopes capture light from a supernova or detectors pick up gravitational waves from colliding black holes, who does that data truly belong to? The scientists who recorded it, the nations funding the observatories, or all of humanity? This isn't just philosophical musing. Real-world tensions already simmer beneath the surface of modern astronomy. Consider the contentious debates over proprietary data periods, where research teams withhold findings for months, sometimes years, before sharing with the broader scientific community. While meant to protect researchers' ability to publish, this practice inadvertently creates hierarchies in cosmic discovery, where access to the universe's secrets depends on institutional privilege rather than collective curiosity. Then there's the matter of cultural sovereignty over celestial observations. Indigenous communities worldwide have tracked stellar phenomena for millennia, embedding supernova and comets in oral traditions long before telescopes existed. When modern science discovers these same cosmic events without acknowledging prior knowledge, it perpetuates a colonial dynamic, treating the sky as terra nullius waiting for Western validation. The recent push for ethnoastronomy, blending traditional star knowledge with astrophysics, offers a promising path forward. Projects like the Maori Star Mapping Collaboration in New Zealand, or the incorporation of Aboriginal astronomical terms into official catalogues, demonstrate how equitable partnerships can enrich our understanding while respecting cultural heritage. Yet the ethics extend beyond Earth's surface. As we develop technologies to manipulate spacetime itself, like proposed gravitational wave mirrors to bounce signals for study, we edge into uncharted moral territory. Would redirecting cosmic echoes for our benefit constitute interference with natural processes? The Outer Space Treaty of 1967 establishes that celestial bodies aren't subject to national appropriation, but says nothing about information or phenomena. Legal scholars now debate whether a supernova's light pattern could be copyrighted if artificially enhanced, or if a detected alien signal's contents might fall under intellectual property laws. These questions sound like science fiction until you realize corporations are already patenting asteroid mining techniques and satellite data monetization schemes. Perhaps the most pressing ethical dilemma lies in how we share these discoveries. When the first image of a black hole's shadow went viral in 2019, it became one of history's most widely distributed scientific visuals, yet the underlying data remained locked behind academic paywalls. Initiatives like open-source astrophysics and citizen science platforms are democratizing access, but the digital divide still leaves billions without meaningful engagement. If stellar echoes carry clues to humanity's cosmic origins, shouldn't their interpretation be as inclusive as possible? The answers we find in Starlight will shape not just our understanding of the universe, but our evolving role within it, making the ethics of how we listen just as important as what we hear. The echoes of collapsing stars aren't just distant cosmic phenomena. They are the universe's oldest storytellers, whispering secrets across billions of years. Every ripple in space-time, every ghostly afterglow of a supernova carries narratives written in the language of physics, chemistry, and time itself. These stellar echoes connect us to events that predate our planet, linking the iron in our blood to ancient supernova and the gold in our electronics to neutron star collisions that shook the cosmos long before life began. They remind us that we're not just observers of the universe, but active participants in its grand recycling process, stardust, that has learned to contemplate its own origins. What makes this cosmic symphony so extraordinary is how much remains undiscovered. Current gravitational wave detectors are like the first crude telescopes, capable of catching only the loudest, closest collisions. Future observatories will reveal thousands more events annually, each a unique chord in the universe's composition. Space-based detectors might uncover mergers from the cosmic dawn when the first black holes formed. More sensitive telescopes could spot the faintest electromagnetic echoes, tracing how heavy elements spread through galaxies, and who knows what surprises await. Perhaps we'll detect entirely new classes of stellar remnants or phenomena that rewrite our understanding of physics. Yet for all our technological progress, the most profound revelation may be philosophical. These echoes collapse time, letting us witness the universe's past as if it were present. A supernova's light arriving today might have begun its journey before Earth formed, while gravitational waves from colliding black holes could carry vibrations from an era when galaxies were just assembling. In listening to these echoes, we're not just studying astrophysics, we're engaging in cosmic archaeology, piecing together the universe's history one vibration at a time. This journey of discovery belongs to everyone, whether you're a professional astronomer analyzing data or simply someone who gazes at the night sky with wonder. These celestial whispers invite us all to listen. So the next time you step outside on a clear evening, remember, the darkness above isn't silent. It's alive with the echoes of stars that died to make our existence possible, their stories still unfolding across the light years. The universe has been singing since the beginning, and with every new detection, every fresh insight, we're learning how to hear the music. If these cosmic mysteries resonate with you, join the conversation below. Share which stellar echo fascinated you most. Was it the gravitational waves from colliding black holes, the glittering remnants of supernova, or the way neutron star collisions forged the universe's heaviest elements? Don't forget to subscribe for more journeys to the edge of space and time. Until our next exploration, keep your eyes and ears open to the universe's endless symphony. The stars may be distant, but their stories are closer than you